Imagine running the cosmic clock backward. The universe is expanding now, so as you wind back the years, galaxies move closer together. Temperature rises, density grows. At 380,000 years before the present, the universe was opaque, a hot pink fog of plasma that no light could escape. Push further. At 1 second, the universe was at 10 billion Kelvin. At a microsecond, quarks and gluons had not yet condensed into protons. At a picosecond, the electromagnetic and weak forces were unified. And at the Planck time, 10 to the minus 43 seconds, the equations that have served us so well stop returning meaningful answers. The numbers run off the edge of their scale. The wall arrives. But the universe did not stop existing at the wall. Something was happening on the other side. And the strangest part is that we can almost see it. The universe leaves fingerprints. The smoothness of the cosmic microwave background, the flatness of space, the seeds of every galaxy that ever formed. Every one of those features carries the signature of a process that acted before the hot beginning we can describe. Make yourself comfortable. Subscribe if you haven't yet, because by the end of this, the wall is going to feel less like a barrier and more like a doorway. Now let's gently fall into this. Part 1. The picture you already have is almost entirely wrong. Almost everyone carries the same picture of how the universe began. Somewhere in the back of the mind, there is a small dot of light against a vast black background, and at some moment in the distant past, that dot exploded outward, sending matter and radiation flying through the surrounding darkness like shrapnel from a bomb. The picture is so familiar that it feels like memory. It shows up in textbooks for children, in popular science films, in the casual analogies that scientists themselves sometimes use when they are tired and trying to explain quickly to a room full of strangers. The dot, the dark backdrop, the flash, the expansion outward into empty space. This picture is wrong in almost every respect. It is wrong in a way that has nothing to do with cutting-edge speculation or unresolved theoretical debates. It is wrong at the most basic level, in the same way that the picture of the Earth as a flat plate sitting at the center of an unchanging sky is wrong. The everyday version of the Big Bang inherits its imagery from human-scale explosions, and at the scale where the actual physics happens, those images break down completely. There was no explosion, and there was no surrounding darkness for the explosion to happen in, and there was no single point, because the early universe was not in a place that had a point. To understand why the casual picture fails, it helps to understand what the Big Bang model actually says. The model does not describe an explosion in pre-existing space. It describes the expansion of space itself. Distances between distant galaxies grow over time, not because galaxies are flying through some external arena, but because the geometry that defines distance is itself changing. The galaxies are, on average, stationary in their local environments. What is moving is the relationship between them. Imagine a rubber sheet with dots painted on it. Now imagine the sheet stretching while the dots themselves do not move relative to the rubber under their feet. The dots end up farther apart, not because they walked, but because the sheet beneath them grew larger. That stretching is what the Big Bang model is actually describing. Not an outward rush of debris, but a change in the fabric on which everything sits. The other piece of the picture that fails is the location. People imagine the Big Bang as an event that happened somewhere, a specific point in space where the explosion occurred, and from which everything else is now flying. But there is no such point. The expansion is not happening from anywhere, because the expansion is not happening through space. It is happening to space. Every point in the universe is, in a real sense, the center of the expansion, because every point in the universe is being stretched away from every other point at the same rate. If you stood at the most distant galaxy you can see in any direction, you would observe the same picture you observe from here, with galaxies receding from you in every direction, with the universe expanding in every direction, with no center, with no preferred location, with no special point that anyone could rightly call the origin. The geometry has no center, because the geometry is the thing that is expanding. This is already strange, and the strangeness has not yet begun. Because the next step is to ask what the universe looked like in the past, when the expansion was less far along, and the answer is that everything we know about the present universe, run backward in time, becomes a hot, dense, opaque state in which the geometry is shrinking, not shrinking toward a point in space, because there is no such point, shrinking everywhere at once, with every region of the universe becoming a hotter and denser version of itself, until at some moment in the distant past the description we have been using begins to break down, and the equations that have served us so well stop returning meaningful answers. The casual picture of the Big Bang fails because it borrows imagery from a world of explosions in air, of bombs in empty rooms, of fireworks against a night sky. None of that imagery applies. The Big Bang was not an event that happened at a place, and it was not surrounded by anything, and the words before and outside are not just hard to apply to it, they may not apply at all. The first thing we have to do, before we can ask what came before, is to clean up the picture of what the Big Bang actually was. And the cleanup is the hardest part, because the casual picture has been sitting in our minds for so long that letting it go feels like losing something we never owned in the first place. The familiar image is comforting precisely because it is familiar. It gives the universe a shape we can hold. What we are about to do is take that shape away and replace it with something stranger, more careful, more honest, something that does not look like an explosion at all. Consider, for a moment, what it means to say that space itself is expanding. The expansion is not motion through a fixed background, because there is no fixed background to move through. The expansion is a property of the geometry. Two galaxies that are separated by 100 million light-years today were, in the past, separated by less than that, not because either galaxy travelled, but because the geometry connecting them was smaller. And in the more distant future, those same galaxies will be separated by more than 100 million light-years, not because either of them will travel further, but because the geometry between them will continue to grow. The galaxies do not move. The space between them grows. This is the most counterintuitive aspect of the model, and it is also the part that allows the universe to make sense without a center. Imagine a slowly rising loaf of bread, with raisins distributed throughout it. As the bread rises, the raisins move farther apart from each other. No single raisin is the center of the rising. No single raisin is moving relative to its local environment. But every raisin sees every other raisin moving away from it, with the most distant raisins receding the fastest. The analogy is imperfect, the loaf has an outside, while the universe does not, but the geometric intuition is right. The universe is rising. Every galaxy sees every other galaxy receding. No galaxy is the center, because the rising is happening everywhere at once. And then, when you imagine this rising in reverse, you get something that is not an explosion at a point. You get something more like the entire loaf compressing toward a smaller and smaller volume, with the raisins approaching each other from every direction at once. The compressed loaf, before the rising began, was a region in which everything was packed close together. Not a point in pre-existing empty space, but a smaller version of the entire system. The Big Bang, in the most accurate visualization, is not a point in space, but a moment in time when the geometry was at its hottest, densest, most compressed configuration. The compression happened everywhere. There is no center to point to. Part 2. What the Big Bang model actually claims. Now we walk slowly through what the Big Bang model actually says. Not the picture, not the analogy, not the imagery, but the claim. The claim is, in one sentence, that the universe began in a hot, dense, expanding phase whose history can be reconstructed back to about a tiny fraction of a second after the start of expansion. That is what the model says. It does not say there was an explosion. It does not say there was a point. It does not say there was anything outside. It says there was an early hot phase, and the laws of physics as we know them allow us to trace that phase forward through cosmic history to the universe we see now, and backward to a regime where those laws themselves begin to lose their grip. The model rests on 3 empirical pillars, and each pillar is supported by independent measurements made by separate teams using separate techniques across multiple decades. The first pillar is the observation that the universe is expanding. This is the discovery most often associated with Edwin Hubble, who in 1929 published a paper showing that the more distant a galaxy, the faster it was receding from us. But the deeper credit belongs to Georges Lemaître, a Belgian Catholic priest and physicist, who in 1927 derived the expansion of the universe from Einstein's equations and proposed what he called the hypothesis of the primeval atom, the idea that the universe began in a single, dense, hot state from which it has been expanding ever since. Lemaitre's work was published in French in an obscure journal and was largely overlooked at the time. Hubble's observation gave the idea empirical teeth. The two together, theory and observation, made the expanding universe a real, testable claim about the world. The expansion is measured through redshift. When light from a distant galaxy reaches us, its wavelength is longer than it was when it was emitted, because the space between the galaxy and the Earth has been stretching while the light was in flight. The amount of stretching tells us how much the universe has expanded since the light was emitted, and the rate of stretching at different distances tells us how the expansion has changed over cosmic time. The relationship between distance and redshift, known as Hubble's law in older texts and the Hubble-Lemaitre law in modern ones, is one of the most consistently measured relationships in all of astronomy. We see it in nearby galaxies, in distant galaxies, in supernovae, in the cosmic microwave background. We see it across more than 100 years of observations. The universe is expanding, and the expansion is accelerating, and the rate has been measured to better than 1%. The second pillar is the cosmic microwave background. This is a bath of microwave radiation that fills the entire sky in every direction with a temperature of 2.72548 Kelvin, just a few degrees above absolute zero. It was predicted in the late 1940s by Ralph Alpher and Robert Herman, working with George Gamow, as the inevitable consequence of a hot Big Bang. If the universe started hot and dense, and has been cooling as it expanded, then there should be a faint thermal afterglow of that early hot phase, stretched by the expansion into the microwave band. The prediction was made and largely forgotten. In 1964, Arno Penzias and Robert Wilson, working at Bell Labs on a different project, accidentally detected the cosmic microwave background as a persistent noise in their radio antenna that they could not eliminate by cleaning, by repairing, by any of the standard troubleshooting techniques. They consulted with the Princeton group that had recently rediscovered Alpha and Herman's prediction, and the noise was identified as the radiation from the early universe. Penzias and Wilson received the Nobel Prize for the discovery in 1978. The cosmic microwave background is, in a real sense, the oldest light we can see. It comes from a moment 380,000 years after the start of expansion, when the universe had cooled enough for free electrons to combine with atomic nuclei to form neutral hydrogen and helium atoms. Before that moment, the universe was a hot, opaque plasma, and photons could not travel freely because they were constantly being scattered by free electrons. After that moment, the universe became transparent, and the photons that had been bouncing around in the plasma streamed outward in all directions. Those photons have been travelling through space ever since, stretched by the expansion of the universe from the visible light they originally were into the microwave radiation we detect today. Every direction you point a sensitive radio telescope, you see the same faint glow, with the same temperature, with the same statistical pattern of tiny variations. The cosmic microwave background is the wall behind which our optical view of the universe cannot go. It is the surface of last scattering, the moment beyond which the universe was too opaque to let light through. The third pillar is Big Bang nucleosynthesis. In the first few minutes after the start of expansion, the universe was hot enough and dense enough for nuclear reactions to occur. Protons and neutrons fused together to form light atomic nuclei, deuterium, helium-3, helium-4, and traces of lithium-7. The predicted abundances of these light elements depend on a small number of parameters that can be measured independently, including the density of ordinary matter and the rate of expansion. The predictions match the observed abundances of these elements in the oldest, most pristine gas clouds in the universe to within a few percent. Hydrogen makes up about 75% of the mass of ordinary matter. Helium-4 makes up about 25%. Deuterium makes up about 25 parts per million. Lithium-7 makes up about 5 parts per 10 billion. These numbers are not adjustable. They follow from the nuclear physics of the first 3 minutes, and they match what we see. Nucleosynthesis is the deepest empirical anchor of the hot Big Bang, because it tells us that the early universe really was hot enough for nuclear reactions to happen, and it gives us a clock against which to calibrate the early expansion history. These 3 pillars: expansion, the cosmic microwave background, and nucleosynthesis are not the only evidence for the Big Bang model, but they are the 3 that have been most thoroughly tested and that are most directly tied to the early universe. Each of them is independently verified by multiple teams using different methods. Each of them gives us a window into a specific moment in the early history of the universe, and together they tell us that the universe really did begin in a hot, dense phase, that the model is not a guess, but a framework supported by multiple cross-checks, and that the picture of the universe as a hot, expanding system is one of the best supported descriptions in all of science. What the model does not say is anything about the absolute first moment. The pillars take us back to a few minutes after the start of expansion. The cosmic microwave background takes us to 380,000 years. The expansion equations, run backward, take us even further to a moment when the universe was so hot, so dense, that our equations themselves begin to break. But the model is not, in itself, a claim about that boundary. It is a description of the hot expanding phase that we can measure. What lies before that phase, what lies behind the wall, is a separate question. It is the question this video is built around. And we are not yet ready to ask it, because we have not yet looked at the wall. Part 3. The wall at the edge of what our equations can say. Now imagine running the cosmic clock backward. You are standing in the present universe, watching galaxies, watching stars, watching the faint microwave glow that fills the sky. You start the clock running in reverse, slowly at first. Galaxies move closer together. The universe gets denser. The temperature of the cosmic microwave background, currently a chilly 2.7 Kelvin, slowly climbs as you wind back the clock, and the radiation that was stretched to microwaves is unstretched back toward visible light, then ultraviolet, then deeper into the spectrum, getting bluer and hotter as you go. 1,000,000 years before the present, the universe was already noticeably warmer and denser than it is now, but it was still recognizably similar galaxies and stars and dust, just packed a little closer. 1,000,000,000 years before the present, the galaxies were younger, brighter, more chaotic, the cosmic web more tangled. 5 billion years before the present, the universe was around 8.8 billion years old. The cosmic web had only just finished assembling itself. The first generation of stars had long since exploded and seeded the gas with the heavy elements that would later form planets and people. Keep winding the clock back. At about 10 billion years before the present, you reach the era of the first galaxies. Massive, irregular, glowing with the light of the first generation of stars that had finished their short, violent lives. Wind back further, and the galaxies dissolve into smaller proto-galaxies, then into clouds of cooling gas, then into a uniform dark medium that fills the universe between the cosmic microwave background and the first stars. This is the cosmic dark ages, the period from the time the cosmic microwave background was released until the first stars ignited and lit the universe back up. The dark ages lasted hundreds of millions of years. During them, the universe was full of matter, but empty of light. Wind further back, and you reach the moment of recombination itself, when the cosmic microwave background was released. At that moment, the universe was a hot pink fog at about 3000 Kelvin, opaque to light, filled with hot ionized gas. Before that moment, our direct view stops. The fog is too thick. We cannot see what happened on the other side using light. But we can still wind the clock back, even if we cannot see directly anymore. We use the equations. We use the physics we know. We push them backward, with all the calibration the pillars have given us, and we ask what the universe must have been like at progressively earlier times. A second after the start of expansion, the universe was a thick, hot soup at about 10 billion Kelvin, full of electrons and positrons and neutrinos and photons. Nuclear reactions were starting to become possible. Before that, the universe was even hotter billions of Kelvin, with the temperature rising as you push the clock further back. A microsecond after the start of expansion, the universe was so hot that quarks and gluons had not yet condensed into protons and neutrons. The universe was a quark-gluon plasma, a state of matter that physicists can briefly produce in particle colliders like the Large Hadron Collider, but only in tiny droplets that last for a fraction of a second. The early universe was filled with this plasma everywhere, at temperatures around 1 trillion Kelvin. The strong force, which binds quarks together inside protons today, was not yet doing its binding work. The quarks were free. A picosecond after the start of expansion, that is, 1 trillionth of a second, the universe was at the electroweak energy scale. The electromagnetic force and the weak nuclear force, which today are distinct forces with very different strengths and ranges, were unified into a single electroweak force. The Higgs field, which today gives most particles their mass, had not yet settled into its current vacuum state. Particles like the electron and the quarks were massless, traveling at the speed of light, with no resistance from the medium they moved through. The universe was a featureless soup of relativistic particles, hotter and denser than any laboratory will ever match. Keep going. Earlier than the electroweak era, the universe enters a regime where our laboratory tests have never reached. We can extrapolate from what we know, but we are no longer measuring directly. The grand unified era, the supersymmetric era, the regimes proposed by various extensions of the Standard Model, none of these has been confirmed by experiment, but each of them might have been a real phase of the early universe. And then, around 10 to the minus 34 seconds, you reach the era of inflation, which we will come back to. And then, even earlier, around 10 to the minus 43 seconds, the Planck time, you reach the boundary of what our equations can describe at all. The Planck time is not a small fraction of a second in any human sense. It is so brief that the question of how long it lasts loses meaning. The Planck length, the corresponding small distance, is about 10 to the minus 35 meters, 100 million billion times smaller than an atomic nucleus. At these scales, the smooth, continuous picture of spacetime that general relativity uses begins to break down, because quantum effects on the geometry itself become significant. The geometry of space and time cannot, in the Planck regime, be treated as a fixed, classical stage on which physics happens. The The stage itself is fluctuating. The fabric is restless. The distinction between particles and the geometry they live in begins to blur. When physicists try to use the equations of general relativity to describe what happens at the Planck regime, the equations produce singularities. Quantities that should be finite densities, curvatures, temperatures, instead diverge to infinity. The most famous of these singularities is the initial singularity, the moment when, in the strict classical extrapolation of general relativity backward, the entire universe is compressed into a single point of infinite density and infinite curvature, with all of physics breaking down at once. This is, for most popular accounts, what is meant by the Big Bang. The point, the infinite density, the mathematical singularity at the beginning of time. But here is the most important thing we will say in this entire video, and it is a thing that many popular accounts get wrong, that singularity is not a real event. It is a feature of our equations failing. It is the equivalent of a road sign that says, "This map is no longer reliable past this point." When we extrapolate general relativity into the Planck regime, the theory predicts its own breakdown. That breakdown is not telling us about reality. It is telling us about the limits of our description. A singularity in the math is a warning that the math has stopped describing the world. It is not a place. It is not a moment. It is a hole in our equations, and we should treat it the way we treat any other failure of a model, as a sign that we need a better one. This is the wall. The Planck regime, 10 to the minus 43 seconds, 10 to the minus 35 meters, 10 to the 32 Kelvin. This is where our equations stop being trustworthy, and this is where the real question of what came before the Big Bang lives. Because if there is anything before, it lives on the other side of this wall, and the wall is not a wall in space. It is a wall in our description. What lies beyond it requires a better theory than we currently have, and the better theory will need to combine general relativity with quantum mechanics, and that combination has been the unsolved problem of theoretical physics for 100 years. For the next several minutes, hold the wall in your mind. The wall is not where the universe ends. The wall is where the words we have built to describe it begin to give out. And beyond the wall, the universe is still doing whatever it has always done. We just have not yet learned to read what it is doing there. The wall is where the question of what came before becomes a question about physics rather than a question about language. And the way past the wall, the way to make the question physical, is the work of the rest of this video. Take a moment to feel the strangeness of the Planck regime, because the strangeness is not just intellectual. It is also visceral, in the sense that anyone who tries to imagine themselves there encounters something that no human imagination can comfortably hold. At the Planck length, the distance between 2 points cannot be measured by any conceivable instrument, because the act of measurement requires light of a wavelength shorter than the distance you are measuring, and light of a wavelength shorter than the Planck length carries enough energy in its own quantum to gravitationally collapse the region you are measuring into a small black hole. The measurement itself disturbs the geometry. Distance, as a concept, stops being well-defined. Time, similarly, stops being well-defined, because any clock you could build to measure intervals of the Planck time would, by its own energy content, distort the geometry it was trying to measure. The Planck regime is not a small place. It is a regime where the concepts we use to describe places stop applying. This is why the singularity in general relativity is not, strictly speaking, a place either. A singularity is a feature of the equations failing. When physicists say the singularity at the Big Bang, they do not mean a literal point where the universe was infinitely compressed. They mean the mathematical breakdown of the description as you push general relativity past its domain of validity. The actual universe, before the equations break down, was very hot and very dense, but it was not infinitely hot or infinitely dense. Those infinities are artifacts. They are what mathematics produces when you ask a model to describe a regime where the model no longer applies. The challenge of pre-Big Bang physics is the challenge of replacing the singularity with something that the equations can actually describe. A better theory, one that combines general relativity with quantum mechanics in a way we do not yet have, would, presumably, not produce a singularity. It would produce a smooth, finite description of what happens in the Planck regime. And whatever that smooth, finite description looks like, it would tell us what came before the Big Bang. The singularity is not the answer. The singularity is the question. And the better theory, when we find it, will replace the singularity with whatever the actual universe was doing at that moment. Part 4. The universe looks as if someone prepared it. Stand back from the equations for a moment and look at what the sky shows us. Not the equations of general relativity, not the abstract math of quantum mechanics, but the actual, measured, observed structure of the universe at the largest scales. What does the universe actually look like when we map it carefully and ask what its shape, its temperature, its composition tell us about its origin? The first thing it shows us is uniformity. Across the entire sky, in every direction, the cosmic microwave background has the same temperature to a precision of 1 part in 100,000. Tiny anisotropies exist at the level of tens of microkelvin, and those anisotropies carry the seeds of all later structure, but the overall picture is one of breathtaking, almost suspicious smoothness. Two patches of sky on opposite sides of the heavens, separated by an angular distance of more than 180 degrees, show essentially the same temperature, the same density, the same statistical properties. This sounds like a small thing. Of course, the universe is uniform on large scales. That is just the cosmological principle, the assumption that no part of the universe is special. But the uniformity is not just a working assumption, it is a measured fact. And it is a fact that, when you look carefully, does not have an obvious explanation. Two regions of the sky that are widely separated today were, in the early universe, on opposite sides of a vast cosmic distance. In a standard hot Big Bang without any additional mechanism, those two regions were never in causal contact with each other before they emitted the photons we now see as the cosmic microwave background. They could not have exchanged information. They could not have come to thermal equilibrium. They could not have agreed on a temperature, and yet they share, to 5 decimal places, the same temperature. This is called the horizon problem, and it is the first of 3 classic puzzles that any account of the early universe has to explain. The horizon problem says, the universe is smoother than it has any right to be. Distant patches that should have been complete strangers, with no way to influence each other, somehow ended up with the same temperature. Either the smoothness is a coincidence of extraordinary improbability, or something happened in the very early universe that allowed those patches to communicate before they were stretched apart by the expansion. The second puzzle is the flatness problem. Space, as far as we can measure it, is geometrically flat. This is what is meant when cosmologists say the universe is flat. In Einstein's general relativity, the geometry of space can be curved positively, like the surface of a sphere, or negatively, like the surface of a saddle, or flat, like the surface of a sheet of paper. The geometry is determined by the total energy density of the universe relative to a critical value. If the actual density equals the critical density, space is flat. If it exceeds the critical density, space is positively curved and closed. If it is less, space is negatively curved and open. Measurements from the Planck satellite in 2018 put the curvature parameter omega sub k at 0 plus or minus 0.005. In plain terms, space is flat to better than 0.5%, and this measurement, taken at face value, points to a strange tuning in the early universe. In a standard hot Big Bang, Any deviation from exact flatness grows over time. If the early universe were even slightly curved, the curvature would have grown enormously by now, and we would see a strongly curved universe today. The fact that we see a flat universe today implies that, at the Planck time, the curvature must have been 0 to 1 part in 10 to the 62nd. This is fine-tuning at a level that demands explanation. Either the initial conditions were astonishingly precise, or something happened to drive the curvature to 0. The third puzzle is the monopole problem. Grand unified theories, extensions of the Standard Model that try to unify the strong force with the electro-weak force at very high energies, predict that the early universe should have produced a relic abundance of magnetic monopoles. These are hypothetical particles that carry a single magnetic charge, like the north pole of a magnet without a corresponding south pole. The predicted abundance, in a non-inflationary cosmology, is high enough that monopoles should dominate the energy density of the universe today. They should be everywhere. They should be the most common particles in the cosmos, but they are not. Decades of experimental searches have found no convincing evidence of magnetic monopoles in any reasonable abundance. The monopoles that grand unified theories predict are missing. 3 puzzles: the horizon problem, the flatness problem, the monopole problem. Together they form a quiet, persistent challenge to the simple hot Big Bang picture. The universe is smoother than it should be, flatter than it should be, and missing the relics it should have. None of these is individually catastrophic. The hot Big Bang can be made to work by simply assuming that the initial conditions were extraordinarily fine-tuned, but that assumption is uncomfortable. 3 independent fine-tunings, each at a level that cries out for explanation, each pointing toward a missing mechanism. The universe at the largest scales looks prepared, not in any mystical sense, not in any sense that requires a designer, but in the precise, quantitative sense that the initial conditions of the hot Big Bang, taken at face value, demand a level of fine-tuning that any honest physicist has to acknowledge is suspicious. Something appears to have set up the early universe in a state that the hot Big Bang model itself cannot account for. Something was already in place, before the equations of the hot Big Bang took over, that produced the smoothness, the flatness, and the absence of unwanted relics. This is the doorway through which the question of what came before the Big Bang first becomes physical rather than philosophical. It is not a vague metaphysical concern about whether time has an absolute beginning. It is a specific, measured, quantitative observation that the early universe behaves like the output of an earlier process that we have not yet identified. The fingerprints are in the sky. They are in the smoothness of the cosmic microwave background, and in the flatness of space, and in the missing monopoles. They are measurable, they are reproducible, they are not going away. The universe is leaving us notes about its prologue, written in the patterns of the oldest light, and the notes say, something happened first. What that something was is the question the rest of this video is built around. The candidates are several. Each candidate makes different claims about what the prologue would have looked like. Each candidate predicts different signatures in today's sky. And the universe, by leaving these fingerprints in its smoothness, its flatness, and its missing monopoles, has handed us a question that is still physical, still testable, still open. The wall at the Planck regime is real. But the wall is not a barrier against knowledge. It is a boundary that the data is pushing against from both sides, from the equations on our side, and from the fingerprints of the prologue on the other side. And what those fingerprints reveal, once you start to look at them carefully, is that the universe is not the silent, indifferent void of the casual picture. The universe is leaving evidence, and the evidence demands to be read. Part 5. Inflation. A vacuum that stretched itself into a cosmos. The leading scientific candidate for what came before the Big Bang is a process called cosmic inflation. The name is poor. It suggests a slow, steady growth, and what actually happens is the opposite, but the name has stuck. Inflation, in the cosmological sense, is a brief era of exponential expansion that occurred in the first tiny fraction of a second of the universe's history, and that ended in the event we call the Big Bang. The idea was proposed by Alan Guth in 1979 while he was a postdoctoral researcher at SLAC, the Stanford Linear Accelerator Center. Guth was trying to solve the monopole problem he was working on, grand unified theories, and was bothered by the prediction of large numbers of magnetic monopoles in the early universe. He realized, in the course of his calculations, that if the early universe had gone through a brief period of exponential expansion driven by a phase transition in a scalar field, the resulting dilution of any pre-existing monopoles would be so extreme that essentially none of them would survive into the observable universe. The monopole problem would be solved. He wrote down the calculation in his notebook in 1979 and labeled it with 3 underlines: spectacular realization. The spectacular realization was the seed of inflation. Guth's initial paper, published in 1981 in Physical Review D, had problems. The phase transition mechanism he proposed did not end cleanly. It produced a universe full of bubble walls and inhomogeneities, not the smooth, structured cosmos we observe. André Linde, in 1982, and independently Andreas Albrecht and Paul Steinhardt, proposed what is called slow-roll inflation, in which a scalar field rolls gradually down a potential energy landscape rather than tunneling through a phase transition. The slow-roll version solves the problems of Guth's original proposal and is, in some form, the basis for nearly all modern inflationary cosmology. What does inflation actually do? It says that, before the universe became the hot, dense plasma we associate with the Big Bang, it went through a phase in which the dominant energy was carried not by particles, but by a scalar field, the inflaton, sitting at a relatively high value of its potential energy. While the inflaton is at this high value, it acts like a temporary cosmological constant. Its energy does not dilute as the universe expands, because the field itself is essentially uniform across space. The pressure of the inflaton is negative, in the technical sense that the equations of relativity require for accelerated expansion. And under these conditions, the universe undergoes exponential expansion. Its size doubles in a fixed interval of time, then doubles again, with each doubling taking the same amount of time as the last. The amount of time per doubling depends on the details of the inflaton potential, but it is typically estimated at around 10 to the minus 34 seconds. 60 doublings, 60 e-folds, in the technical jargon is enough to take a region that started smaller than a single proton and stretch it to a size much larger than the entire currently observable universe. 60 doublings, in less than a trillionth of a trillionth of a trillionth of a second. The expansion factor is roughly 10 to the 26. The universe, in a moment, becomes vastly larger than anything we can currently see. Now hold this picture in your mind. What does inflation look like from the inside? The first thing to notice is that the universe is almost empty. Whatever ordinary matter and radiation existed in the patch of space that ended up inflating, that matter and radiation has been diluted to essentially zero by the exponential expansion. After 60 e-folds, there is roughly 1 particle of pre-existing matter in the entire volume of the now massive inflating region. The universe is, in matter terms, an almost perfect vacuum. The only energy is the inflaton field itself, which sits at a nearly uniform value across the inflating space, carrying the dark energy that drives the expansion. The second thing to notice is that the universe is smooth. Whatever inhomogeneities existed in the pre-inflation patch have been stretched to scales much larger than the inflating region. Any structures, any density variations, any features that existed before inflation have been smoothed out by the same mechanism that diluted the matter. The universe ends inflation in a state of extraordinary uniformity, with the only remaining variations being the quantum fluctuations of the inflaton field itself. These quantum fluctuations are crucial. Even though the inflaton sits at a nearly uniform value, quantum mechanics requires that there be small uncertainties in that value at every point, small jitters around the average, set by the Heisenberg uncertainty principle. As inflation proceeds, these quantum jitters are stretched along with the rest of space. What started as microscopic uncertainties in the field value become, after 60 e-folds, classical density variations on cosmic scales. The quantum jitter at one moment in the inflating universe becomes, by the end of inflation, the seeds of every galaxy that will ever form. Imagine, for a moment, being inside an inflating region. The picture is strange. Space is expanding so rapidly that any 2 points are separating from each other faster than light. Locally, light still moves at its usual speed, but globally, the geometry is stretching faster than light can keep up with it. You cannot see anything beyond a small region around you, because light from further away cannot reach you against the headwind of the expansion. The universe around you looks like a smooth, almost completely empty vacuum, with the only visible features being the tiniest of quantum ripples in the inflaton field, and even these are invisible to anything resembling a normal observer. There is no light from stars, because there are no stars yet. There is no warmth, because there is no warmth. The inflaton field carries energy, but that energy is not heat in any conventional sense. The universe during inflation is calm in a way that nothing in our world is calm, because it is empty in a way that nothing in our world is empty. And then, at some moment, inflation ends. The inflaton field reaches the bottom of its potential, starts to oscillate, and its energy is transferred through a process called reheating into ordinary matter and radiation. The energy that had been carrying the universe through exponential expansion becomes the energy of particles and photons. The universe transitions, in a moment, from an empty, inflating space to a hot, dense plasma. The quantum fluctuations that had been stretched to cosmic scales are now embedded in the temperature variations of the new hot plasma. The universe begins the conventional hot Big Bang phase that we have already described. In this picture, the Big Bang is not the beginning. It is the end of inflation. It is reheating the moment when the inflaton field gave up its energy and the universe became hot. Everything we think of as the Big Bang, the hot, dense, expanding state, the cosmic microwave background, nucleosynthesis, the structure formation, all of that comes after inflation ends. Inflation is the prologue. The Big Bang is the curtain rising on the play. Inflation, as a theory, has been spectacularly successful. It solves the horizon problem because the entire observable universe was once contained in a tiny patch that was in causal contact before inflation began. The smoothness across the sky is the smoothness of that tiny patch stretched to cosmic scale. It solves the flatness problem because the same exponential stretching that smooths the universe also flattens its geometry. Any pre-inflation curvature is diluted to nearly zero by the sheer scale of the expansion. It solves the monopole problem because any pre-inflation monopoles are diluted to essentially zero abundance. And it generates the spectrum of density fluctuations that match what we observe in the cosmic microwave background to many decimal places. If inflation is the prologue to the Big Bang, then what came before the Big Bang is not a fireball or a darkness or a singularity. What came before the Big Bang is an inflating vacuum, an almost empty, exponentially expanding space carried by the energy of a scalar field, painted only with the quantum jitter that will become every galaxy. That is a picture. It is a specific, calculable, in principle, visualizable picture of what the universe was doing in the moments before the hot Big Bang. and it is the picture supported by most of the evidence we currently have. Whether that picture is the whole answer is a separate question, but as a candidate for what came before the Big Bang, inflation is the most empirically successful candidate we have. Let's spend a few more moments inside the inflating phase, because the imagery is one of the strangest things in modern physics, and it deserves to be lived with for a while. Picture yourself, with whatever stretch of imagination is required, as an observer inside the inflating region during inflation. You cannot really be there. No human-scale observer can exist in such an environment, because there is no matter from which to construct an observer. But for the sake of the visualization, suspend that objection and place yourself there. What do you see? You see nothing. There are no photons of visible light. There is no temperature in any conventional sense. The inflaton field carries energy, but that energy is uniform across the space around you. There are no density variations large enough to perceive. There are no objects. There are no scales by which to measure distance, because the geometry around you is so dramatically different from the geometry of any familiar place that the comparisons fail. But more than the absence of things, there is the relentless expansion. The distance between any 2 points around you is doubling every 10 to the minus 34 seconds. If you could mark 2 points in the space ahead of you, you would watch them separate, even though neither point is moving. The geometry between them is growing. The space ahead of you is fleeing from you faster than light. The light cone of any event you might consider is shrinking, because the expansion outpaces light itself at the global scale, even though at every local point, light still moves at its usual speed. The only thing that has any structure anywhere around you is the quantum jitter of the inflaton field. Microscopic ripples appearing and disappearing within the bounds of the uncertainty principle, the way virtual particles appear and disappear in any quantum vacuum, but here on a stage that is stretching them slowly into something larger. That stretching is the key. Each quantum ripple, once it is stretched to a scale larger than the Hubble radius, the maximum distance light could travel in 1 Hubble time gets frozen. It can no longer evolve back to zero. It becomes a classical perturbation. By the time inflation ends, 60 E-folds of expansion later, the stretched ripples are the largest features in the universe. They are the seeds of every galaxy, every cluster, every void. Standing inside the inflating region, you would not see these ripples directly. They are too small at any moment, even though they are growing, but you would, if you understood the physics, know that you are witnessing the creation of structure, not through any visible process, but through the silent, relentless stretching of microscopic uncertainty into cosmic scale. The visualization is humbling because it is so completely unlike anything human experience prepares us for. There is no warmth, because there is no warmth in any conventional sense. The inflaton field is not at a temperature in the way ordinary matter is at a temperature. There is no time in the usual sense, because the Hubble timescale is so short that any clock you could imagine would be torn apart faster than it could tick. There is no scale, because the expansion is dilating everything by such enormous factors that any reference length you fix in your mind disappears into the past. And yet, in this almost completely empty, almost completely uniform, almost completely undefined regime, something is happening. The quantum jitter is being preserved. The seeds are being laid, and when inflation ends, the universe will rapidly transition to the hot, dense state we recognize as the Big Bang, with all of those preserved quantum ripples imprinted as density variations in the new plasma. This is the picture inflation gives us of what came before the Big Bang. It is not nothing. It is a specific, calculable, in principle, visualizable state. The universe before the Big Bang was an inflating vacuum. The vacuum was almost empty. The vacuum was carrying the energy of a scalar field. The field was producing quantum ripples that, stretched by the expansion, would become the structure of the cosmos. The Big Bang itself was the moment when the field's energy converted into ordinary matter and radiation, ending the inflating phase and beginning the hot phase. Everything we observe, every galaxy, every star, every atom descends from that transition. And the inflating vacuum that preceded it was the necessary prologue, the stage on which the seeds of our universe were planted before the play we know began. Part 6. But what started inflation? Inflation, for all its success, comes with a problem that is impossible to ignore. The problem is the same problem that any account of cosmic origins eventually has to face. If inflation is the prologue to the Big Bang, then what is the prologue to inflation? What started the inflaton field at the high value of its potential where the exponential expansion could begin? What set the initial conditions of the inflating phase? In short, if inflation explains the Big Bang, what explains inflation? The first version of this problem is the initial conditions problem. For inflation to start, the inflaton field needs to be sitting at a relatively high value of its potential, with low kinetic energy over a patch of space that is at least roughly the size of a Hubble volume at the inflationary energy scale. That is a specific configuration. It is not the most generic configuration the universe could be in. If you imagine a random distribution of possible initial conditions for a scalar field across space, the probability that any particular patch is in the configuration required for inflation to start is small. Some calculations have suggested it is exponentially small. The inflating patch is, in a real sense, a special initial state, one that itself demands explanation. The second version of the problem is the past incompleteness theorem, proved by Arvind Borde, Alan Guth, and Alexander Vilenkin in 2003. The Borde-Guth-Vilenkin theorem states, with mathematical rigor, that any spacetime in which the average Hubble expansion is positive throughout its history must be past incomplete. There must be a finite past boundary beyond which the geometry, taken on its own terms, cannot be extended. In plain language, inflation cannot have been happening forever. Whatever inflation we observe must have had a beginning. If you try to trace the inflating phase backward in time, the math says you eventually reach a boundary, and that boundary is not just a feature of our equations, it is a feature of the geometry itself. This is a sharper, more mathematically rigorous version of the singularity theorems that Hawking and Penrose proved in the 1960s and 70s. Those earlier theorems showed that classical general relativity, applied to an expanding universe, predicts a singularity in the past under broad conditions. The Borde-Guth-Vilenkin theorem extends this to inflation. Even if inflation smooths out the classical singularity, the inflating phase itself cannot be eternally past. There is still a boundary, and at that boundary, our description fails again. So if you ask what came before the Big Bang, and the answer is inflation, then the next question, what came before inflation, is unavoidable, and it does not have a clean answer. Several proposals have been made. Each of them faces its own difficulties. Each of them pushes the question of origins one step further back, but none of them eliminates the question entirely. The structure of the problem seems to be that whatever mechanism produced the universe we see, that mechanism itself has to come from somewhere. And the somewhere recedes as we improve our theories, but it does not disappear. The first proposal is eternal inflation, which we will treat in detail later. Eternal inflation says that, while any individual region of inflating space must have had a beginning, the overall inflating multiverse, the larger structure within which our particular Big Bang sits, does not have to be past incomplete in the same sense. The argument is subtle and not universally accepted. Some calculations suggest eternal inflation is itself past incomplete. Others suggest it might be eternally self-reproducing in a way that softens the past incompleteness theorem. The debate is ongoing. The second proposal is quantum cosmology, in which the entire universe, including any inflating phase, has a wave function rather than a classical history. In this picture, the question of what came before the inflating phase becomes a question about the boundary conditions of the wave function of the universe, not about an earlier physical time. We will return to this. The key point for now is that quantum cosmology offers a way to soften the past incompleteness theorem by saying that, near the boundary, the classical description is replaced by a quantum one, and the question of before is reinterpreted as a question about quantum amplitudes rather than physical histories. The third proposal is bouncing cosmology, in which the universe did not begin with inflation, but with a contracting phase that bounced and became expanding. We will explore this in detail later as well. The bouncing models offer an alternative to inflation, with its own visualization of what came before the Big Bang. The fourth proposal is the Hartle-Hawking no-boundary proposal, which we will also explore. In this picture, the universe simply has no past boundary at all. The geometry rounds off smoothly in a way that makes the question of before geometrically ill-posed. What unites these proposals is a common recognition. The inflationary phase, on its own, does not answer the deepest question. It pushes the question back. It explains the smoothness, the flatness, and the missing monopoles. It generates the density fluctuations that became galaxies. It is the leading candidate for the immediate prologue to the Big Bang. But it does not answer the question of where the universe came from. It only redescribes the question at a different scale. This is not a failure of inflation. It is a feature of the deep structure of the question itself. Asking what came before the Big Bang is, in a real sense, asking what came before time, and that question may have a different status depending on which theory of quantum gravity we eventually adopt. The current frontier of the question is, in part, a question of how to push past the Bordet-Guth-Vilenkin boundary in a controlled way, how to describe what happens at the past edge of inflation, how to handle the quantum gravity regime that lies on the other side. For now, what you should hold in your mind is this. Inflation is the best supported candidate for what came before the hot Big Bang. It looks like an almost empty, exponentially expanding vacuum painted with quantum ripples. It solves the horizon, flatness, and monopole problems. It generates the seeds of galaxies. It is the leading scientific account of the prologue, but it is not the final answer. It is one piece of a longer chain, and the chain continues to recede as we look deeper. The wall at the Planck regime is still there. Inflation pushes back where the wall is, but it does not eliminate the wall. The question of what came before keeps moving because the answer keeps revealing new questions. Hold that. The engine that made us is still running, but the engine itself was started by something earlier, and the earlier thing is still hidden behind the wall. The wall keeps moving. The looking has to keep moving with it. Part 7. Eternal inflation and the bubble universes beyond our horizon. If inflation explains the Big Bang, and the question recedes to what explains inflation, one of the most striking answers is that nothing has to explain it ending, because in many versions of the theory, inflation never ends. It just keeps going, forever. Everywhere except in small bubbles where it happens to stop. The bubbles are universes. We are inside one. This idea is called eternal inflation. It was first noticed by Paul Steinhardt in the early 1980s, then developed more fully by André Linde in 1986. Linde realized that the quantum fluctuations in the inflaton field, which are essential for generating the seeds of galaxies, also have a less comfortable consequence. The fluctuations are not always small. At any given moment, in any given region of inflating space, there is some probability that the quantum fluctuations push the inflaton field upward back toward a higher value of its potential. In those regions, the field's potential energy increases, the conditions for inflation are reinforced, and the expansion continues. Now think about what this means at the level of the inflating region as a whole. Most regions of the inflating space, most of the time, are slowly rolling down their potentials toward the end of inflation. In some small fraction of regions, the quantum fluctuations push the field back up. In those regions, inflation continues longer than it would have classically. Those regions also continue to expand exponentially, so even though they make up a small fraction of the total inflating volume at any given moment, their volume is growing faster than the regions where inflation has ended. After a while, the fraction of the total volume that is still inflating grows, not shrinks. The inflating regions are winning the race. The result is that, even though inflation ends in any individual patch, it never ends across the entire inflating space. The inflating background is always larger than the regions where inflation has ended. Bubbles of post-inflation universe, like our universe, nucleate from time to time, but they cannot catch up to the growth of the inflating background that surrounds them. Inflation, once started, never stops globally. It only stops locally, in small bubbles. Our universe, in this picture, is one such bubble. Inflation ended in our local patch, about 13.8 billion years ago. That ending event is what we call the Big Bang. The hot plasma that filled our bubble is the byproduct of the inflaton field's energy converting to particles and radiation at the end of inflation. Our observable universe is the inside of this bubble, as it has expanded and cooled over the subsequent 13.8 billion years. But outside our bubble, beyond the cosmic event horizon that limits what we can see, the inflating background is still inflating. Other bubbles are still nucleating. Some of those bubbles may be tiny, just barely cooled enough to support classical physics. Some may be enormous, far larger than our observable universe. Some may have ended with different values of the fundamental constants, different electron mass, different fine structure constant, different cosmological constant. Some may not support atoms at all. Some may not support time and space in any form that we would recognize. The eternally inflating multiverse, in this picture, is a population of bubbles with different physical properties, all embedded in an inflating background that continues to produce new bubbles forever. This picture has profound implications. The first is that the universe, meaning the larger inflating structure, is much larger than we can see. The observable universe is a single bubble. Beyond it, in the inflating multiverse, there are uncountably many other bubbles, with uncountable possible histories. The second implication is that the constants of nature in our universe may not be unique. In other bubbles, with different values of the fundamental parameters, the laws of physics may look different. Our universe is one realization. Other realizations exist, separated from us by an inflating background that we cannot reach. The third implication is for the question of what came before the Big Bang. In an eternally inflating multiverse, the answer is the inflating background. Our Big Bang was the moment our bubble nucleated from the inflating background that still surrounds us. Before our Big Bang, in the inflating background, the universe was expanding exponentially, almost completely empty, with the inflaton field carrying the dark energy that drove the expansion. After our Big Bang, our bubble cooled into the hot plasma we measure. The inflating background, meanwhile, is still inflating. It has been inflating for as long as our bubble has existed, and it will keep inflating long after our bubble has cooled into its eventual heat death. The picture is strange, but it is not arbitrary. Eternal inflation falls out of the equations of slow-roll inflation under reasonable assumptions about the quantum fluctuations of the inflaton field. It is not an extra hypothesis layered on top of inflation. It is a consequence of standard inflation when you take the quantum fluctuations seriously. Many cosmologists who developed the theory have been uncomfortable with the consequence. Linde, who first noticed it, has spent decades arguing about its implications. Guth, the originator of inflation, has been more cautious. Steinhardt, who co-developed the theory, has become one of its strongest critics and has spent the last 20 years developing alternatives. The eternal inflation prediction is one of the most consequential and most disputed claims in modern cosmology. If eternal inflation is right, then the question what came before the Big Bang has a specific, calculable answer: the inflating background that still exists just beyond our cosmic event horizon. The before is not in the past. It is also in the present, in the elsewhere. The engine that made us is still running, in places we cannot see, producing other bubbles like ours, with potentially different physics, with their own observers, with their own Big Bangs, with their own questions about what came before. Hold that for a moment. The phrase before the Big Bang assumes that before refers to an earlier time in our universe's history. But in eternal inflation, before is also a elsewhere. The inflating background does not exist only in our past. It exists also, right now, just outside our horizon, in regions that are causally disconnected from us. The engine that produced our universe is still operating. We are inside one product of that engine. The engine itself is still running. This is not a metaphor. It is a direct prediction of the leading inflationary models. The volume of inflating space in eternal inflation is currently larger than it has ever been, doubling on a timescale of about 10 to the minus 34 seconds. In the time it took you to read this sentence, an unimaginable amount of new inflating space came into existence. By the time you finish this video, the inflating background will have grown by a factor that defies meaningful description. The engine, if eternal inflation is right, has no off switch and no end. What does this look like? From outside the multiverse, it would look like an inflating space with bubbles nucleating inside it, small islands of post-inflation universe scattered throughout an ever-expanding inflating sea. From inside any particular bubble, like ours, it would look exactly like what we see: a finite, observable universe with a cosmic microwave background marking the edge of what we can detect, and beyond that edge, an inflating background that is invisible to us because we cannot reach it. The visualization is humbling. The universe is not the small, comfortable cosmos that we see through our telescopes. The universe, the larger structure of which our cosmos is one piece, is unbounded, eternally inflating, producing new universes forever, with our observable universe being just one bubble among an uncountable population. This is one of the most consequential and most contested predictions of modern cosmology, and it is the answer that eternal inflation gives to the question of what came before the Big Bang. Before the Big Bang, the inflating background existed, and it still exists, and it is still inflating just beyond what we can see. Part 8. The Bouncing Alternative. The universe before was our universe backwards. Not everyone is happy with inflation. Even some of the physicists who helped develop the theory have come to think that its problems outweigh its successes, and they have spent decades developing alternatives. The leading alternative to inflation is bouncing cosmology, a family of models in which the universe did not begin with an inflationary expansion, but with a contracting phase that bounced and became expanding. In these models, the Big Bang is not a beginning, it is a bridge. The universe before the Big Bang was a previous contracting cosmos, and the bounce, the moment when contraction reversed and became expansion, is the event we call the Big Bang. The earliest bouncing cosmology proposals date to the 1930s, when Richard Tolman considered cyclic universes that alternated between expansion and contraction. Tolman ran into a serious problem. In a classical universe with ordinary matter, each cycle would accumulate more entropy than the last, leading to a thermodynamic memory that, run backward, implied an infinite past universe with zero entropy. That seemed unphysical. The Tolman problem, as it came to be called, was a major obstacle to early bouncing cosmologies, and the idea fell into disfavor for several decades. Modern bouncing cosmologies have several mechanisms for getting around the Tolman problem. The most influential modern version is the ekpyrotic universe, proposed by Justin Curry, Bert Overett, Paul Steinhardt, and Neil Turok in 2001. In ekpyrotic models, the contracting phase before the Big Bang is dominated not by ordinary matter, but by a scalar field with a specific kind of potential energy, one that makes the field's equation of state extremely stiff. A stiff equation of state has the unusual property that, during contraction, it dilutes anisotropies and inhomogeneities relative to the dominant component of the universe. This is the opposite of what happens in a generic collapsing universe, where anisotropies grow chaotically as the collapse precedes the so-called BKL behavior, named after Belinsky, Kalatnikov, and Lifshitz, who first described it in the 1970s. In an ekpyrotic contracting phase, the universe gets progressively smoother as it shrinks. The smoothing is dynamical, driven by the stiff equation of state, and it solves the same problems that inflation solves. The horizon problem, the contracting phase, has time to smooth the universe. The flatness problem, the stiff equation of state dilutes curvature, and the monopole problem, relics are diluted by the stiffness. At the bottom of the contracting phase, the universe is smooth, flat, and free of relic particles, just as inflation predicts at the end of its expansion phase. Then the bounce happens, and the universe becomes the hot, expanding, smooth, flat cosmos we observe. What does the bounce look like? In ekpyrotic models, the bounce is not a literal mathematical singularity, but a smooth transition driven by the dynamics of the scalar field, or, in some versions, by higher dimensional effects from string theory. The universe shrinks to a minimum scale factor, typically much larger than the Planck scale, so quantum gravity effects do not have to be invoked, then expands again. The bounce is a single, specific event in the universe's history. It is not a singularity. It is not a moment of infinite density. It is a turning point at which the rate of expansion goes from negative contraction to positive expansion, with the scale factor passing through a minimum value. What does the universe look like during the contracting phase? In ekpyrotic models, the contracting phase looks very different from our expanding phase. The dominant energy is the scalar field with its stiff equation of state. The universe is, during this phase, smoother and emptier than it is during expansion. As contraction proceeds, the universe shrinks, but it does not grow hotter in the chaotic way that a generic collapsing universe would. The stiffness of the scalar field's equation of state keeps the contraction orderly. By the time the universe reaches the bounce, it has been smoothed to a state that resembles the late stages of inflation, flat, smooth, with the seeds of structure encoded in quantum fluctuations of the scalar field. Loop quantum cosmology, developed by Abhay Ashtekar and his collaborators starting in the early 2000s, provides a different mechanism for a bounce. In loop quantum cosmology, the classical Big Bang singularity is replaced by a quantum bounce at very high but finite density. The mechanism is the discreteness of geometry at the Planck scale, which causes the standard Friedmann equations of general relativity to be modified by a correction term that becomes important only at densities near the critical density ρc, approximately 0.41 Planck densities. The correction term effectively makes gravity repulsive at extreme density, reversing the collapse and producing a bounce. Before the bounce, in loop quantum cosmology, the universe was a contracting cosmos that approximately mirrored our expanding cosmos running in reverse, with quantum gravity effects becoming significant only at the highest densities. The picture of the universe during the contracting phase in loop quantum cosmology is striking. The universe before the bounce looks much like our universe today, but running backward. Galaxies would be falling toward each other rather than apart. The cosmic microwave background would be blue shifting rather than red shifting, with the temperature rising as the scale factor falls. At earlier times in the contracting phase, which in the reverse timeline is later in our backward picture, the universe would be hotter, denser, with the early ionized plasma being followed by the recombination of atoms, then by a contracting cosmic microwave background, then by the same dark ages we have in our expanding phase, then by the era of the first stars and galaxies. The contracting universe, in loop quantum cosmology, is in some sense a time reverse of our universe, at least until close to the bounce, where quantum gravity effects begin to matter. For Sundown science viewers, the key thing to understand about bouncing cosmologies is that they offer a radically different visualization of what came before the Big Bang. In the inflationary picture, before the Big Bang was an almost empty inflating vacuum. In the bouncing picture, before the Big Bang was a previous contracting universe, possibly with structure, possibly with galaxies and stars in some models, possibly looking very much like our own universe in reverse. The Big Bang is a transition between these two phases, not a creation event. This is a major shift in the imagery. The before in bouncing cosmologies is recognizable. It is not a featureless, inflating vacuum. It is a contracting cosmos with a clear history, with its own laws of physics, with its own arrow of time. Before the Big Bang, in this picture, the universe was a real place. It was running in a direction we would consider backward, but it was running. It had structure. It had history. And the moment we call the Big Bang was the moment when that history reached its turning point and started over. There are open questions, of course. Bouncing cosmologies are not without problems. The Tolman problem, even in modern bouncing models, requires some mechanism for entropy to be reset or hidden across the bounce. The contracting phase has to be smooth enough and stable enough to actually reach the bounce without falling into chaotic collapse. The transition through the bounce has to preserve the quantum information needed to seed the structure we observe, and the predicted signatures, the specific fingerprints that bouncing cosmologies should leave in the cosmic microwave background and in the spectrum of primordial gravitational waves, are still being calculated and compared to observations. But, as an alternative to inflation, bouncing cosmologies are taken seriously by a significant minority of cosmologists. Steinhardt, who helped develop slow-roll inflation in the 1980s, has spent the past 2 decades developing the ek-pyrotic and cyclic alternatives. Turok, Ashtekar, Bogerwald, and others continue to refine the bouncing models. The competition between inflation and bouncing cosmologies is one of the active frontiers in modern cosmology, and it is one of the places where the question of what came before the Big Bang remains genuinely open. If the inflationary answer is an inflating vacuum painted with quantum ripples, the bouncing answer is our universe in reverse, with a turning point at the moment we call the Big Bang. Part 9. Conformal cyclic cosmology, the heat death of a previous cosmos. There is another bouncing style cosmology that deserves its own treatment because the picture it offers is one of the strangest and most counterintuitive that any modern cosmologist has seriously proposed. The idea is called conformal cyclic cosmology, and it was developed primarily by Roger Penrose starting in the mid-2000s. Penrose is one of the giants of 20th century mathematical physics, co-author of the Penrose-Hawking singularity theorems, developer of twistor theory, recipient of the Nobel Prize in 2020 for his work on black holes, and his proposal for what came before the Big Bang is built on a single, elegant, and deeply strange mathematical insight. The insight is this. In the very far future of our universe, after all the stars have burned out, after all the matter has been swallowed by black holes or otherwise decayed, After all the black holes themselves have evaporated through Hawking radiation, the universe will consist almost entirely of massless particles, photons, and possibly gravitons spread thinly across an inconceivably vast volume of space. In this remote future state, there is no longer any structure, no galaxies, no stars, no atoms, no black holes, just stretched, low-energy radiation filling an almost empty void. Penrose noticed that this remote future state, mathematically, has a special property. With no massive particles left, there is no longer any meaningful distinction between large scales and small scales, because all the particles travel at the speed of light, and there is no fixed scale set by the masses of particles to compare distances to. The geometry of the universe in the far future, in this state, has a conformal symmetry. You can rescale distances by any factor, and the physics remains the same. This conformal symmetry is the key. Penrose argued that the remote future of our universe, after the heat death, is mathematically equivalent through a conformal transformation to the Big Bang of a new universe. The very far future of one cosmic aeon, viewed through the lens of conformal geometry, looks exactly like the very early universe of the next aeon. The Big Bang of our universe is, in this picture, the conformally rescaled heat death of a previous universe. And the eventual heat death of our universe will, in turn, become the Big Bang of a future universe. Hold this picture in your mind. Before the Big Bang of our universe, there was another universe. It had its own age, perhaps 13 billion years, perhaps more, perhaps less. It had its own history, its own stars, its own galaxies, its own civilizations, possibly its own intelligent observers asking what came before. That universe lived through its history, watched its stars die, watched its black holes form and grow and eventually evaporate, watched its matter decay into radiation, and watched itself approach the cold, dilute, almost featureless state of its own heat death. And then, when the universe had become so cold and so spread out that no meaningful scale remained, the conformal symmetry of its geometry allowed it to be reinterpreted as the hot, dense, freshly born state of a new universe. The next aeon, our Big Bang. The mathematical move is called a conformal rescaling. It is a specific operation on the metric of spacetime, the mathematical object that defines distances and times. A conformal rescaling stretches or compresses all distances by a factor that can vary smoothly across space, but it preserves the angles between directions and the causal structure of spacetime. Two events that were time-like separated remain time-like separated. Two events that were space-like separated remain space-like separated. The light cones at every point remain light cones. What changes is the scale. In the very far future of one aeon, the universe is mathematically equivalent through such a rescaling to the very early universe of the next aeon. The infinite future of one becomes the infinitesimal past of the other. The two are stitched together by the conformal map, with the heat death of the previous aeon becoming the Big Bang of the next. If conformal cyclic cosmology is right, then what came before the Big Bang is, quite literally, the heat death of a previous universe. The universe before the Big Bang was a vast, cold, almost completely empty space filled with stretched, low-energy photons that had been traveling for trillions of years through the dilute remains of a previous cosmos. There were no galaxies, there were no stars, there were no atoms. There was only the long, slow fade of an old universe approaching its end. And then, through the conformal rescaling, that fading universe became our Big Bang. The photons of the previous heat death became the high-energy photons of our early hot phase. The cold, dilute state became, through the rescaling, the hot, dense state. The end of one aeon became the beginning of the next. This is a different visualization from inflation, and a different visualization from the ordinary bouncing models. In conformal cyclic cosmology, before the Big Bang, there was a cosmos very different from our own, not contracting, not inflating, but slowly dying. The before is a previous universe at its end, not its beginning. And the cycle continues forever, with each universe's heat death becoming the next universe's Big Bang, in a chain of eons that has no first member. There are predicted signatures. Penrose has argued that gravitational waves from supermassive black hole mergers in the previous aeon, transformed through the conformal rescaling, should leave specific patterns in the cosmic microwave background of our aeon. He has claimed, in a series of papers from 2010 onward, to have detected these patterns, low variance circles, in the cosmic microwave background, small bright spots, Hawking points, attributed to the final evaporation of the previous eon's supermassive black holes. Independent analyses by the WMAP and Planck teams have been less convinced. The claimed features are at the edge of statistical significance, and they are consistent with the predictions of standard inflationary statistics. The signatures are debated. Penrose himself acknowledges that the case is not yet decisive, but argues that the predicted patterns are real and that they are evidence of a previous eon. Even setting aside the empirical claims, the conformal cyclic picture is one of the most evocative visualizations of pre-Big Bang physics. Imagine being inside the previous eon at its end. You are floating in an immense, almost empty space. The last black holes have just evaporated, releasing their final bursts of Hawking radiation. The cosmic microwave background of that universe, already stretched by trillions of years of expansion to wavelengths far longer than any radio wave we have built, fades into an undetectable, almost zero-temperature glow. There is no light, there is no matter, there is no clock, because there are no massive particles to define a rest frame. Time, in a real sense, has lost meaning, because the conformal symmetry of the geometry no longer distinguishes between long durations and short ones. And then, the conformal rescaling. The vast, almost empty universe is, through a mathematical operation that has nothing to do with motion or with time, reinterpreted as a small, dense, hot universe, the early stages of a new eon. The same physics, the same photons, the same gravitational waves, but viewed through a different scale, they are no longer the dying glow of an old universe. They are the bright, hot beginning of a new one. The Big Bang. This is the conformal cyclic cosmology picture of what came before the Big Bang. It is the strangest of the candidates we have looked at, in some ways the most poetic, and it is also one of the most contested. The mathematics is real, the empirical claims are debated, but the picture is unforgettable. Before the Big Bang, in this view, was the heat death of a universe like ours, and before that heat death was a long, slow fade of another cosmos through its own history. The chain of eons has no first member. The cosmos has been recycling itself through conformal rescaling forever, with each aeon's heat death becoming the next aeon's Big Bang. The engine of the cosmos is, in this picture, eternal, but not in the way eternal inflation is eternal. It is eternal as a sequence of eons, each one a complete universe, each one connected to its predecessor and successor by the conformal symmetry of the very late and very early states. Time itself, in this picture, is the chain. There is one more thing worth saying about the conformal cyclic picture, because it carries an implication that is easy to miss. If the previous aeon was a real universe, with its own complete history, then somewhere in that universe, at some point during the long stretch of time, before the stars all died and the black holes all evaporated, there may have been observers, beings made of matter, looking up at their sky, asking the same question we are asking now. What came before our Big Bang? They would have had their own cosmic microwave background, their own galaxies, their own physics, their own questions. They would have built their own instruments. They would have noticed the same horizon problem, and the same flatness problem, and the same missing monopoles, because those problems are features of any universe that follows from a hot beginning. And they would have proposed their own candidates for what came before, including, possibly, their own version of conformal cyclic cosmology, pointing to the aeon before theirs as the answer. In this view, the question, what came before the Big Bang, is one that has been asked in countless universes by countless observers across countless eons. We are not the first to ask it. We will not be the last. The chain of eons is, in some real sense, also a chain of asking, and our place in the chain is one moment, in one universe, in one ongoing process that has been recycling itself forever and will continue to do so. The asking is part of the universe's behavior, in this picture, just as much as the conformal rescaling. Wherever observers can exist, they will eventually ask. And wherever they ask, the answer the previous aeon left them is the same: a heat death, stretched into a beginning, an end mapped into a start. The cosmos handing each generation of observers the residue of the previous cosmos and inviting them to read it. We are, if conformal cyclic cosmology is right, one such generation. The reading is ours to do. Part 10. Brains, Quantum Cosmology, and Universes Born from No Spacetime. We have looked at 3 candidates so far for what came before the Big Bang. The inflationary candidate, with its almost empty, exponentially expanding vacuum; the bouncing candidate, with its contracting cosmos running approximately backward into our own; the conformal cyclic candidate, with its previous eon dying into our beginning through a geometric rescaling. There are more. 2 more candidates deserve attention here, because they push the imagery even further away from the conventional picture. The first is the ekpyrotic braneworld picture, in which the Big Bang is a collision between higher dimensional structures. The second is quantum cosmology, in which the Big Bang is not a moment in time at all, but a boundary condition on the wave function of the universe. The braneworld picture is built on ideas from string theory. In string theory, the fundamental constituents of matter are not point particles, but one-dimensional vibrating strings, and the consistency of the theory requires extra spatial dimensions beyond the 3 we observe. The most popular versions of string theory require 10 dimensions of space-time, 9 of space, and 1 of time, with the extra 6 spatial dimensions either compactified to very small sizes or constrained by other mechanisms. In some versions of string theory, 3-dimensional surfaces called branes can exist within higher dimensional spaces, with the strings of ordinary matter attached to particular branes by their endpoints. The brane on which our matter lives is, in this picture, our universe. The full 10 or 11-dimensional space within which our brane is embedded is called the bulk. Other branes can exist in the bulk, and the bulk can have a geometric structure of its own, a 5th dimension, or higher, in which the branes move. In the ekpyrotic braneworld picture, developed by Curie, Overut, Steinhardt, and Turok, starting in 2001, the Big Bang of our universe is the moment when our brane collided with a neighboring brane in the higher dimensional bulk. Before the Big Bang, the 2 branes were widely separated in the higher dimensional space, with the bulk between them. Over a long period of higher dimensional time, the branes slowly approached each other, with various exchanges of fields and ripples across the bulk. When the branes finally collided, the kinetic energy of their impact converted into the hot plasma of the early universe what we observe as the Big Bang. In this picture, before the Big Bang, there were 2 branes approaching each other in a higher dimensional space. What this would have looked like to any observer that could have existed, and the question of whether such an observer could exist is itself complicated, is 2 vast 3-dimensional sheets drifting through a larger space, with the bulk between them carrying various fields and excitations. The collision was not a sudden event in any local sense. It was the conclusion of a slow, billions of years of bulk time process in which the branes had been approaching each other across a higher dimensional gap. The braneworld picture is striking because it gives the Big Bang a physical mechanism in terms of higher dimensional dynamics. The Big Bang is not a beginning of everything. It is a collision between specific structures in a larger space. Our universe is one brane among possibly many. The bulk between the branes is real, and the question of what came before the Big Bang has a calculable answer. Two branes were approaching each other. The quantum cosmology picture is even more abstract. In quantum cosmology, the universe is not described by a classical history with a definite space-time geometry. Instead, the universe is described by a wave function, a quantum mechanical object that assigns amplitudes to different possible configurations of the universe. The boundary conditions on this wave function determine what kinds of histories are possible. Different proposals for the boundary conditions give different predictions about the early universe. The most famous of these proposals is the Hartle-Hawking no-boundary condition proposed by James Hartle and Stephen Hawking in 1983. The Hartle-Hawking proposal says that the universe has no boundary in the past, that the geometry rounds off smoothly in a way that, when extended into imaginary time, becomes a compact, regular shape with no singular edge. Asking what came before the Big Bang in the Hartle-Hawking picture is, as Hawking famously put it, like asking what is north of the North Pole. The question is ill-posed. There is no before. The geometry simply ends, in the same way the surface of a sphere ends at its pole. Another proposal is the Vilenkin tunneling from nothing condition, proposed by Alexander Vilenkin starting in 1982. In the Vilenkin picture, the universe quantum tunnels into existence from a state of no classical space-time at all, a state in which there is no geometry, no time, no fields, no matter, only the abstract wave function of the universe with its boundary conditions. The probability of the universe spontaneously appearing in some specific configuration is given by the wave function evaluated at that configuration. The Big Bang, in this picture, is the moment when the universe quantum tunneled from nothing, in the technical sense of no classical space-time, into something, a small inflating universe. What did the universe look like before the Big Bang in quantum cosmology? The honest answer is that the question may not apply. The visual vocabulary we use to describe how something looks, light, color, space, time, all depends on the existence of a classical space-time. In quantum cosmology, before the Big Bang, there was no classical space-time. The wave function was defined on a space of possible geometries, not on any one specific geometry. There was no specific moment, no specific configuration, no specific look. There was a quantum amplitude for various possibilities, and the Big Bang was the moment when one of those possibilities, our universe, was realized. This is the strangest of the candidates. It is the one where the question itself begins to lose its grip. If quantum cosmology is right, then before the Big Bang may not refer to an earlier time, because time itself emerged from the wave function at the moment of the Big Bang. The before may not exist, in the same sense that north of the North Pole does not exist. This is also where the question of how the universe really looked before the Big Bang has its sharpest answer. In some candidates, inflation, bouncing models, conformal cyclic cosmology, the universe before the Big Bang had a specific, in principle, visualizable appearance. In other candidates' quantum cosmology, certain emergent space-time proposals, the universe before the Big Bang did not look like anything at all, because the structures that would make a look possible were themselves emergent. The question becomes, which of these is right? The answer the universe gives us if it gives us any answer at all, will come through the signatures left in today's sky. Each candidate predicts a different pattern in the cosmic microwave background, in the spectrum of primordial gravitational waves, in the statistics of the largest cosmic structures. The observational program of the next several decades, CMB Stage 4, the Lightbird satellite, the LISA gravitational wave interferometer, future 21 centimeter surveys of the early universe, is designed in part to look for these signatures. We may, in our lifetimes, see the universe begin to choose between the candidates. We may see the fingerprints of inflation, or of a bounce, or of a previous aeon, or of a brane collision become statistically distinguishable. We may even see the case for quantum cosmology become stronger if, for example, the predicted signatures of inflation, bouncing, and conformal cyclic models all fail to appear at the level expected. What you should hold in your mind is that the question is not closed. The candidates are real candidates. The signatures are predicted signatures. The data is still coming. The universe is, in this very moment, in the act of revealing its origin to us through patterns in light and gravity that we have not yet learned to read fully. The looking is still happening. The wall at the Planck regime is still there. But the wall is not a barrier against knowledge. It is a boundary that the data is gradually pressing against from both sides. Part 11. The fingerprints in the sky and the instruments that hunt them. Every candidate prologue to the Big Bang is, in principle, distinguishable from the others by the signatures it would leave in the universe we observe today. The candidates are not just philosophical alternatives. They are specific physical theories that make specific predictions about what we should see in the sky if they are right. The job of observational cosmology over the next several decades is to look for those signatures with progressively better instruments and to see which candidate, if any, the universe has actually used. The most direct signature of inflation is a stochastic background of primordial gravitational waves. Inflation, with its exponential expansion, would have amplified quantum fluctuations of the gravitational field in the same way it amplified quantum fluctuations of the scalar inflaton field. The result is a faint, near-scale invariant background of gravitational waves filling the universe today. These waves leave a characteristic imprint on the polarization of the cosmic microwave background, a pattern called B modes, which has a curl-like topology that ordinary density fluctuations cannot mimic. The hunt for primordial B modes has been one of the most intense observational campaigns in modern cosmology. The BICEP and Keck experiments at the South Pole have, over the past 15 years, set progressively tighter upper bounds on the amplitude of the B-mode signal. As of 2024, the bound on the tensor-to-scalar ratio, R, a number that quantifies the amplitude of primordial gravitational waves relative to the density fluctuations, is less than 0.036 at 95% confidence. This bound rules out some of the simplest inflationary models, including the simplest forms of large-field chaotic inflation, but it remains consistent with a broad family of slow-roll potentials. A detection of primordial B modes at any level would be one of the most important discoveries in physics, and it would be a direct fingerprint of inflation. The non-detection so far is a constraint, not a refutation. The next generation of experiments, including CMB Stage 4, a ground-based observatory with thousands of detectors planned to come online in the next several years, and the Lightbird satellite, scheduled to launch in the late 2020s, will push the bound on the tensor-to-scalar ratio by a factor of 10 or more. If inflation is right, and the energy scale of inflation is high enough, these instruments should detect primordial B modes. If they do not detect anything, the constraint on inflationary models will tighten further, and the empirical case for some alternatives will strengthen. Bouncing cosmologies make different predictions. In ekpyrotic models, the stiff equation of state of the contracting phase suppresses the amplification of long-wavelength gravitational waves. The result is a tensor spectrum that is blue, meaning more power at high frequencies, less at low frequencies, and that would be invisible in the cosmic microwave background, but potentially detectable in space-based gravitational wave interferometers, like LISA, the Laser Interferometer Space Antenna, scheduled to launch in the 2030s. A blue tensor spectrum detected by LISA, but invisible in the cosmic microwave background, would be a strong fingerprint of a bouncing prologue. Bouncing cosmologies also predict specific patterns of non-Gaussianity deviations from the Gaussian statistics of inflation in the cosmic microwave background and in the distribution of galaxies. The Planck satellite has measured the non-Gaussianity parameter f sub nl, local to be minus 0.9 plus or minus 5.1, which rules out the most extreme bouncing models, but remains consistent with the simpler ones. Future galaxy surveys, particularly the Sphere-X satellite mission and the Square Kilometre Array Radio Observatory, both expected in the next decade, will improve these constraints by orders of magnitude. Conformal cyclic cosmology predicts no primordial gravitational waves from inflation, because there is no inflationary phase in the standard CCC picture. A detection of primordial B modes by CMB stage 4, or Lightbird, would be strong evidence against CCC. CCC also predicts specific patterns in the cosmic microwave background circular structures and bright spots that Penrose attributes to the previous aeon. The empirical status of these predictions remains contested, with the cosmological community largely skeptical but not dismissing the possibility entirely. Quantum cosmology, in some versions, predicts subtle modifications to the spectrum of cosmic microwave background fluctuations at the largest scales modifications that depend on the choice of boundary condition on the wave function of the universe. These predictions are at the edge of statistical significance because the largest scales are limited by cosmic variance, the fact that we observe only one realization of the universe, and the largest scales have the fewest independent samples. Even with perfect instruments, we may never be able to definitively distinguish a Hartle-Hawking universe from a Vilenkin universe based on the cosmic microwave background alone. The constraints have to come from combining multiple observations. Eternal inflation, beyond just the inflationary signatures, predicts the possibility of bubble collisions. If our observable universe is one bubble in an eternally inflating multiverse, and if other bubbles nucleated nearby in the inflating background, then our bubble could in principle have collided with a neighboring bubble at some early time, leaving a signature in the cosmic microwave background. The signature would be a localized feature, perhaps a disk-shaped temperature or polarization anomaly at a specific location in the sky. Searches for such signatures have so far come up empty, but with progressively tighter constraints. The Mersini-Houghton interpretation of the cosmic microwave background cold spot in Eridanus as a bubble collision signature remains debated. The Hubble tension, the discrepancy between H0 measurements from direct distance ladder methods, about 73.04 km per second per megaparsec, and from cosmic microwave background-based inference, about 67.36, is one of the most serious empirical tensions in cosmology. Some early universe modifications, including early dark energy, modified recombination, and certain non-standard pre-Big Bang phases, can in principle reduce the tension. Whether the Hubble tension is a signal of new physics in the early universe or a systematic error in one or both measurements is one of the major open questions in cosmology in 2024 and 2025. Take all of this together. The observational program is rich. The signatures are specific. The candidates are distinguishable, in principle, by what they predict for the cosmic microwave background polarization, the spectrum of primordial gravitational waves, the statistics of large-scale structure, and the specific anomalies at the largest scales. The next decade or two will see significant improvements in all of these measurements. The universe is, in this very moment, in the act of being interrogated by the most sensitive instruments humans have ever built about the question of what came before the Big Bang. And here is the thing to hold on to. The interrogation is not, fundamentally, an exercise in human curiosity. It is the universe answering, in the only way the universe ever answers, through the patterns of light and gravity that reach us from the oldest moments. The patterns are there. The instruments are getting better. The candidates are making predictions. The data is accumulating. We may, within our lifetimes, see the universe choose between the candidates. We may see the fingerprint of inflation, or of a bounce, or of a previous aeon, or of a brain collision become statistically clear. We may even see the question of what came before begin to have a real, definite answer, not in the speculative sense, but in the empirical sense. The looking is still happening. The universe is still revealing itself. And the most remarkable thing is that we have access, in principle, to the answer. The fingerprints of the prologue are there, in the sky, available to be measured by instruments that humans build and operate. The universe is not hiding the answer in some inaccessible place. It is putting the answer in the cosmic microwave background, in the spectrum of gravitational waves, in the statistical pattern of galaxies. It is giving us the data. It is up to us to learn how to read it. Part 12. The Wall and the Mirror, and Why the Looking itself has an Edge. Now we come to the close. The question that opened this video, how did the universe really look before the Big Bang, has, by this point, fractured into several possible answers, each with its own visualization, each with its own predictions, each with its own status as a scientific theory. The inflationary answer, before the Big Bang, the universe was an almost empty, exponentially expanding vacuum, painted only with the microscopic ripples of quantum fluctuations in the inflaton field. The expansion was so rapid that distances doubled on a timescale of about 10 to the minus 34 seconds. The universe ended inflation in a state of extraordinary smoothness, with the quantum ripples stretched to cosmic scales where they became the seeds of every galaxy that would ever form. The bouncing answer, before the Big Bang, the universe was a contracting cosmos, possibly one that, run in reverse, resembled our own. Galaxies were falling toward each other. Temperature was rising as the scale factor fell. The universe approached the bounce, the moment we call the Big Bang, when quantum gravity effects, or a stiff equation of state, reversed the collapse and turned contraction back into expansion. The conformal cyclic answer, before the Big Bang, there was a previous aeon, a complete universe with its own history, its own galaxies, its own observers, its own 13 or so billion years of cosmic evolution. That universe lived through its history, watched its stars die and its black holes evaporate, and approached its own heat death. And then, through the conformal symmetry of its remote future geometry, that heat death became, mathematically, the Big Bang of the next aeon, our aeon. The braneworld answer, before the Big Bang, two three-dimensional sheets brains were drifting through a higher dimensional space, slowly approaching each other. The Big Bang was the moment of their collision, the moment when the kinetic energy of impact converted into the hot plasma of the early universe. The quantum cosmology answer, before the Big Bang, the question itself loses its grip. Time and space, in the strict quantum cosmological view, did not yet exist as classical concepts. The universe was a wave function, an abstract quantum object with amplitudes for various possible histories. The Big Bang was the moment when one of those possibilities was realized, when classical spacetime emerged from the quantum substrate. These 5 answers are not all equally well supported. Inflation, with its empirical success in explaining the horizon, flatness, and monopole problems, and in predicting the spectrum of cosmic microwave background fluctuations, is the leading candidate. The bouncing alternatives are taken seriously, but have not yet matched inflation's predictive power. Conformal cyclic cosmology is intriguing but contested. The braneworld proposals are mathematically elegant but observationally unverified. Quantum cosmology is foundational but offers a different kind of answer, one that dissolves the question rather than answering it directly. But notice what is striking about this list. Every one of these candidates is a serious scientific proposal. Every one of them makes specific predictions that can, in principle, be tested. Every one of them lives within the realm of physics, not philosophy, not metaphysics, but physics, with equations and observables and falsifiable claims. The question of what came before the Big Bang is no longer a question about the limits of language or about the existence of a first cause. It is a question about which specific physical mechanism, inflation, bouncing, conformal rescaling, brane collision, or quantum tunneling, actually produce the universe we observe. And the universe, through the fingerprints it leaves in the cosmic microwave background, and in the gravitational wave background, and in the statistical patterns of galaxies, has given us a way to ask the question empirically. The observational program of the next several decades, CMB Stage 4, Lightbird, LISA, the Square Kilometre Array, Sphere X, and many others will press the question harder than it has ever been pressed. The universe will, slowly, give us its answer. But there is a deeper edge to the question, and we should be honest about it before we close. Even if every signature is measured to perfect precision, even if every candidate prologue is distinguished from every other, even if the data tells us with no remaining ambiguity that inflation or bouncing or conformal rescaling produce the universe we observe, even then, the deepest question may remain: why did this particular mechanism operate? Why does the universe contain a scalar field with the right potential for inflation, or a stiff equation of state phase for ekpyrotic contraction, or the conformal structure that allows cyclic rescaling? Why does anything exist at all? Why is there something rather than nothing? These questions may not be answerable by observational cosmology. They may not be answerable by physics at all. They may sit beyond the wall in a way that no instrument can reach, and that is okay. Acknowledging the limits of what we can know is not a failure. It is the beginning of honesty. The universe is, in this view, larger than the words we have built to describe it, and the words will continue to give out at the deepest layers, no matter how much better our equations become. But here is the thing that should land, at the end. The wall at the Planck regime is real. The deeper wall, at the question of why there is anything at all, is also real. And yet, between the two walls in the region where physics still operates, we have made enormous progress. We have learned to read the fingerprints of the prologue in the patterns of light and gravity from the oldest moments. We have built candidates that make specific predictions. We have designed instruments that, within our lifetimes, will give us answers that previous generations could not have imagined asking for. We are, in this very moment, in the act of looking at what came before the Big Bang, not in any speculative sense, but in the empirical, physical, measurable sense. The engine that made us is still running. Inflation continues, in the eternally inflating multiverse, beyond our cosmic event horizon. The cycle of eons continues, in the conformal cyclic picture, with each universe's heat death becoming the next universe's Big Bang. The bouncing universe continues, with its alternating cycles of contraction and expansion. The wave function of the universe continues to evolve, with possibilities being realized in the present moment as they were realized at the Big Bang. The engine is not just an event in our past, it is a process that, in some sense, is still happening, and so is our looking. The looking is part of the process. The universe is revealing its origin to us, slowly, through the patterns it has left in the sky and through the equations we have learned to write. The looking does not end. The wall is not a barrier against the looking. It is a boundary that the looking presses against, century after century, instrument after instrument, refinement after refinement. The wall recedes as we look harder. It does not disappear, but it does not stop the looking either. So when you look up at the sky tonight, when you see the stars and the planets and the faint band of the Milky Way, hold this in your mind. Some of the photons reaching your eye are carrying information about a moment older than you can fully imagine. The cosmic microwave background, invisible to your unaided eye, but detected by satellites overhead, is the oldest light we can see, 380,000 years old at its emission, 13.8 billion years old at its arrival, stretched by the expansion of space from visible light into microwave radiation along the way, and hidden in the statistical pattern of that ancient light is the fingerprint of what came before. The signature of inflation, or of a bounce, or of a previous aeon, or of a brain collision, or of a quantum origin. The universe is, in this very moment, telling us its story. It is telling us in faint, statistical, hard-to-read patterns, but it is telling us, and the instruments we are building will, in the years and decades to come, learn to read those patterns with progressively greater precision. The universe before the Big Bang was not nothing. The universe before the Big Bang was something specific, with a specific structure that left specific signatures. The signatures are there. We are learning to read them. And the answer, whatever it turns out to be, will be one of the deepest discoveries in the history of human understanding. Not because it will resolve every question. Some questions sit beyond the looking. But because it will be the moment when we first read, with statistical confidence, the story the universe has been trying to tell us since before there was a sky to look up at. The wall is not where the universe ends. The wall is where the words we have built to describe it begin to give out. And beyond the wall, the universe is still doing what it has always done, leaving fingerprints we have not yet learned to read fully, in light and gravity that have been travelling toward us since the oldest moments. The engine is still running. The looking has its own edge. And between those two, the most important work of cosmology continues, in laboratories and observatories and on hilltops, where people still occasionally stand and look up at the sky and wonder how it all began. The wondering is part of the engine. The looking is part of the running. The universe and the people watching it are, in the deepest sense, the same story still being told.